Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at the Lewis bending equation. This video is part of a lecture series on Mechanical Design 2 and this video is part of Module 2. So we're going to get started with some introduction to spur and helical gears a little bit and looking at what we're going to talk about today in more depth as we go along. So to start off with, I have a few different things that we're going to be doing in this module 2, throughout this module. So to start with, one thing that we're going to be doing is analysis and design to resist bending failure of teeth and pitting failure of surfaces. So this is the two things that we're going to focus on in this module is, first of all, the analysis, and design to resist bending failure. So what we're trying to achieve is to resist bending failure and pitting failure. And today, and in this video, we're going to be talking about bending failure, but we'll talk about pitting failure later on as well. So how does a tooth fail in bending? Well, one way that it fails in bending is the tooth stress exceeds the yield strength or bending endurance strengths. So these are two things that we can measure on the tooth, which are the yield strength as well as the bending endurance strength. And we're able to see, well, if the stress exceeds that strength, or if we build it to a certain strength and it exceeds it, then we can break the tooth. Now, for surface failure, the surface failure usually happens when contact stress exceeds the surface endurance strength. So essentially when the strength of the surface is not high enough to hold all the stress there is from contact, we can have surface failure. And this contact is happening between different teeth. So we always want to bring it back to thinking about two teeth hitting each other and essentially pushing against each other and figuring out, does the tooth survive or does the tooth fail? And the two ways in which it fails are shown above. So we're going to analyze a few different methods to do so. We're going to be using the Lewis bending equation for bending. We're also going to be discovering in this module the AGMA approach. And what AGMA stands for is American Gear Manufacturers Associations, and they've developed a whole methodology as to how to figure out if a tooth is going to survive and how to design teeth and analyze teeth for gearboxes. So it's going to be very, very helpful. But to start with, we kind of want to bring it back to the Lewis bending approach and how it was initially started, all this. So some of the assumptions that we're going to do throughout this module and we're going to have throughout this module is just to simplify all of our analysis, we're going to assume that we have a single pressure angle, okay, of 20 degrees. And we're also going to assume that we always have full length teeth. And this was part of our discussion in module 1, where we discussed that we could have different pressure angles. In this chapter, in this module specifically, we're going to restrict ourselves to these numbers. Now, these numbers are just arbitrary, and obviously we can change them, and we could do analysis for the same thing, but in the end, the analysis would be exactly the same. So it's just to simplify a little bit of the calculations and charts that we have to use for all these approaches that we're going to learn. So we're going to start with thinking about how a tooth is thought about in terms of analysis. So if we look at a tooth, and I have this diagram on the left here, which is in your handout and available to you. If we have a gear and we draw one tooth on this gear, okay, just trying to draw a tooth on the gear, then we can kind of look at the tooth and say, okay, well, let's focus on bending first, okay, and we're going to focus on bending. So we're not going to look at surface for now, we're just going to look at how bending occurs and how we can see if the tooth resists bending. Okay, So one thing we can do is we can try and model the tooth as something that we already know from statics, uh, from our study of statics, and something that we already know from our study of engineering. And so what we want to do is we want to start with potentially simplifying the gear tooth to some geometry that we already know, and then kind of apply the equations of that geometry to an actual gear tooth and potentially apply some correction factors. So back in 1892, when we started using gears for industrial purposes, people started getting interested into how we could analyze gears and how we could make sure that the forces that the gears went through would mean that they wouldn't break. And so this person called Lewis created his Lewis bending equation based on the idea that a gear would behave kind of like a cantilever beam. And this cantilever beam would have a force, WT, on the end of it, or essentially modeling as if it had a force at the tip of the tooth. And that would give us the worst case scenario in terms of what a tooth went through when it was going into contact with another tooth. And by this, we could kind of figure out, well, what is the strength of our tooth? What is the stress that is felt by our tooth? And is that enough to, is the design strong enough to withstand what forces it's going to go through? So doing that, what what Lewis did was he basically started developing equations as if a gear tooth was modeled exactly like a cantilever beam. So if we look at the diagram below, we have an example of a cantilever beam. So this is in 2D. So it's a drawing in 2D, and this F is actually the face width. So I'm going to put that F is equal to face width, not force in this case. And WT is actually the force or the tangential force. Okay, you can see that there's a superscript T, so it's W with a superscript T. It's actually exactly the same thing as W lower t. So this WT is equal to the WT we've been using in earlier videos. They're equivalent. Essentially, you can use either or, and they mean exactly the same thing. So think about the face width as a cross section that's cut into our beam. So if you wanted to draw this in 3D, what it would be is it would look something like this. Okay, so in 3D, our diagram would look something like this. And of course, we would have our face width being the width of the beam, essentially. If I were to draw another face width here just for illustration purposes, the face width would be all throughout. Okay, so that's what this F with the shaded color means. It's not the best diagram, but it is the diagram that is used for this illustration. But essentially, if you have a 3D, you have F as the face width, T as the thickness or the height, essentially, and then L as the length of the beam. And based on these cross-sectional dimensions, so we're going to write cross-sectional dimensions. We have F, T, and L as these cross-sectional dimensions. And so if we remember from our analysis of statics, and if you have had a statics class before, or you've done some statics studies before coming into this type of level of analysis, we can say that the stress is equal to M times Z over I, where M is the bending moment, Z is the distance from neutral axis to a point of interest. And I is called the second moment of inertia. Okay, and typically we think of a tooth as initially when we start analysis of our cantilever beam, we can say that the simplest beam would be a rectangle, so we can use the second of moment of inertia of a rectangle, and we get that that's equal to base times height cubed over 12, which is also equal to ft cubed over 12. So from that, we can start analyzing our system. Now, the other thing that we need to know is the distance from a neutral axis to a point of interest. So that does not mean the distance from the edge of the beam to the far side of the beam. It actually means that it is the neutral axis in our case is actually the middle of this beam. Okay, so this is the neutral axis, and I'll draw it all the way through. Okay, so the neutral axis is the middle of the beam, and the point of interest is actually, and I'll draw it in red here, is actually t over 2 away. So we have that z in our case would be equal to t over 2. Okay, so based on that, we can then write the equation for stress would be equal to, for this specific beam, would be equal to m times t over 2 divided by ft cubed over 12 based on our geometry. And that would simplify, if we work out all the math, would simplify to 6m over ft squared. So now that we have that, we can start working a little bit closer as to what's happening. So the other thing we can say is that we know that m is the bending moment. So what is m equal to? Well, m could be substituted by, so m is going to be equal to the moment, the bending moment, and we know that there's a wt at the very end or at the tip of the tooth, multiplied by L would give us the bending moment as for the cantilever beam. So the cantilever beam is fixed on this side and we're looking for the bending moment. So M would be equal to WT. And again, it can be superscript or subscript. It's the same thing multiplied by L. Okay, which means that based on our diagram and based on the figures on our diagram, we can now find the stress as 6WT times L over Ft squared. And now what we can do is we can analyze our system and design our system so that the force, the strength is higher than the stress seen. Now going a little bit further than this and actually mapping this onto a tooth geometry as opposed to just a cantilever beam, what Lewis did is he actually went a little bit further than this and decided to map everything on a tooth as opposed to just a beam. So by doing this, what happened is he essentially, and let me copy over a diagram that's also in your handout. So he essentially looked at a tooth and kind of geometrically simplified the tooth to match kind of what we were seeing with our cantilever beam. Okay, and there's some distances here that are a little bit different, but essentially he has that as an information. Now, he knows that there is a W that's occurring at a certain angle or at the pressure angle of 20 degrees. He knows there's a WT and a WR, so those are the tangential and radial components. And based on the geometry, he starts drawing triangles as well. And what we're going to do is we're going to look at this diagram and kind of simplify it even more to just leave the triangles in place that we have just to understand what's happening. So if we take this triangle and we take that at the top, there is a force WT and WR, we have this force, and then we have a distance L that is from here to this point on the tooth, where we have this bottom surface of the tooth. Then we have a point A here. We have that this distance is T over 2. Okay, so if we look at this distance on this side of the tooth, we have a distance of T over 2. And then we have a similar triangle that gets developed at the bottom, and we'll talk about why this triangle is important, with a distance x from the bottom. So we can see that we have a distance x from the bottom here that's highlighted in our diagram as well with an x. And what we can do is we're really going to just use this as a geometrical proof of something, and to try and get our values to modify slightly to something a little bit more simplistic. But essentially what Lewis did is he took this diagram, and there's one more line that I'm going to draw, is this construction line here. I'll draw it in red just so that we can see it, that it's designed after. Okay, so we have this construction line, and what we want to look at is there's going to be what we call a law of similar triangles. And what this law of similar triangles tells us is that essentially the two triangles that we see in the figure, so the top triangle and the bottom triangle, are actually geometrically similar because they both share a 90-degree angle, and they both share point A together. They're just in a different direction. So what we can say is that the ratio of L over T over 2, okay, is going to be equal to the ratio of T over 2 divided by X. Okay, and we're going to use this later. So it doesn't really make sense right now, but we're going to use this later to substitute back into our equation and understand how we can figure out the length of an actual tooth based on the X value as well, and based on the design of actual gear teeth usually. So we can rearrange this to say that X is equal to T squared over 4L, or L is equal to T squared over 4X. Okay, so we have this, and so what we can do is we can say that if we recall our sigma value, we can say that sigma is equal to 6WT times L over FT squared, which, if we rearrange this equation, we can put WT over F, and remember F is not a force, it's the face width, okay, times, and I'm going to rearrange this mathematically, we're going to have 1 over T squared over 6L. And again, this wouldn't make sense as just doing this for the purpose of doing it, but there is a reason why we're doing this. It's to come up with a simplified equation based on different geometry that we need to know. And Lewis was doing this derivation when he was developing his system of equations and his system to solve essentially a bending problem for gear teeth, for the geometry of gear teeth. So moving further than this, we have WT over F, so we keep simplifying this. Then we're going to split our T squared over 6L into two different terms. So we're going to have 1 over T squared over 4L, and you see where this is going a little bit. Okay, the T squared over 4L can now be substituted by X if we want to. And then this is going to be 1 over 4/6. So in order to get rid of the 6, you need to have a conversion of 1 over 4/6, or this could also be written as 1 over 2/3. Okay, so going further than this, then we can say that this is equal to WT over F times 1 over X times 1 over 2/3. And finally, we can write that sigma is equal to WT over f times 2/3 times x. So if we know this x value for our teeth, or if we design our teeth with different x values based on the length of our tooth and all that stuff, we only need to know the depth of x in order to find our system. So we have this new equation that says that that sigma is equal to wt over f 2/3 times x, and this x value can be a parameter of design for our gear teeth. Now, one extra thing that Lewis did after this is he said, well, let's use this x and come up with a definition for x that we standardize. So we're going to standardize the way we design teeth, and it's going to have a different x value every time. The problem with the x value is that it's a distance, and it's a number that is a distance. So if you have different gear teeth sizes, it doesn't really make sense to have a design for every gear tooth sizes. So what he decided to do was to take this equation and multiply it by p over p. And this p over p is a lowercase p. Okay, and so this is, if we go back to our module 1 information, so going back completely at the very start, we go back to lowercase p, we see that lowercase p is called the circular pitch, and it's the distance from one tooth to another along the pitch circle. So now we have a distance from one tooth to the next along the pitch circle, and we can now normalize our x value with a p value. So we'll talk about that in a second, but essentially what we can do is we can say, well, if we have a value that's something x over p, then that value is constant for any size of gear. And if you design your gear with this constant, which we're going to call the Lewis form factor, so it's like essentially a shape factor for your gear, then you will always have your analysis correct with this shape factor. So going back to the notes now, so we have this, so we can say Lewis, what he did is he created a term called the Lewis form factor, and he decided to take the 2/3 into account, so we didn't have this 2/3, this awkward 2/3 in the equation, and he said that y is equal to 2x over 3p. Okay, and based on that, he then could substitute into the equation. He could say that sigma is equal to wt divided by f times lowercase p, so one of the p's would cancel, the other p would stay, multiplied by y. And this is the Lewis form factor. Now, going further, what he did is he created this first form factor, but he wasn't really satisfied with his first form factor, so he decided to, because circular pitch is not always easy to find and not always easy to figure out. So what he decided to do was to go a step further and find and do one for the diametral pitch. So he created another term for the diametral pitch with capital P. So if you have capital P, which diametral pitch is used in all of gear teeth, when you're sizing gear teeth, you just talk about the diametral pitch of the tooth so that you know immediately how many number of teeth per diameter you have. So that's N over D. And we know that the relation between uppercase and lowercase p is equal to pi. So we can say that p is equal to pi over lowercase p. Okay, so capital, and this one's lowercase. So this is recalling equations from module 1. We can now say that this lowercase y that he had come up with was going to be equal to y was going to be equal to pi times capital Y, which is a new term, and we can call it the new and current Lewis form factor. Okay. And the reason why we're doing this whole derivation is to kind of understand where Lewis came from. We're not really going to use this in any evaluation or in any um, typical problems that you would have. You wouldn't go through and rederive all of Lewis's equations, but it's important to know where they come from. And so doing a little bit more algebra and math, you would get that capital Y is equal to 2x times capital P over 3, and therefore we could rewrite our sigma equation as W sub T times P over F times capital Y. And based on this equation, so just to make sure that we have both equations, so this is our new Lewis form factor. And what we're going to have to accompany us throughout this module is also a formula sheet. And in this formula sheet, you'll see that the Lewis bending equation is here at the top. There's a slight change to the Lewis bending equation, and we'll talk about it in a second. But all of your equations are going to be in this formula sheet, as well as all your charts that you need to have. Now, if we go to the second page of this formula sheet, you'll see that based on the number of teeth, you can then solve for different Lewis form factors. So if you know that your gear, for example, has 22 teeth, it would have a capital Y of 0.331. So you don't have to calculate the Lewis form factor every time. You do need to interpolate it between tooth numbers, but there's a bunch of teeth numbers here that are already available, and then you could find your sigma based on the Lewis form factor. So based on a typical gear tooth geometry, you can find your Lewis form factor directly. And then the only thing you would need to know is the thickness of your tooth, or the face width of your tooth, and the capital P, or the diametral pitch, and then your WT, and you could find your sigma. So very, very easy to solve for sigma. So moving back to our lecture really quickly. So a few things that we want to summarize of about the Lewis equation and the Lewis bending equation is we want to summarize a few things, and then we want to eventually start doing examples in the next part or the next video. So let's summarize a few things about the Lewis bending equation. So it assumes beam bending. So this is either, you can view it as a limitation or how he pictured it in 1896, but essentially it assumes beam bending, so it's not perfect because a gear tooth is not always in beam bending. Now, the other thing that he assumes is that the greatest force occurs at tip of tooth. So in the analysis that we saw, we see that if we go back to our handout, we can see that the WT is placed at the tip of the tooth. Now, in real life, we know already from our module 1 that the tooth actually has a contact throughout the tooth, and it rolls on the other tooth. Whereas here, we assume that the greatest force occurs at the tip of the tooth, and we assume that it's like a point load at the end. It's not a distributed load at all. So definitely different type of problem than we usually have. Typically, the force would move along the tooth, along the involute profile as it touches another gear, and then it would move to the next gear. So that's definitely limitation, right? So we're writing some of the limitations that there are. Third thing that we're assuming is teeth do not share load. So this is another big assumption, is we talked about how the contact ratio, or the M sub C of teeth, should always be greater than 1.2, meaning that there should always be at least 20% of the contact that should be done with two teeth overlapping each other. That is essentially not the case in this type of analysis. So Lewis bending equation assumes that the teeth do not share the load. It just assumes that one tooth is taking all the load. And in some ways, with these three assumptions, we can design with these three assumptions in mind, and this methodology worked pretty well at over designing, because in the end, we were thinking of a worst case scenario. So when Lewis was designing this, he was coming up with an equation that would over design some gear teeth essentially. So he would always be on the safe side because it was over designing, even though it wasn't really designing for the exact parameters that he was actually looking for. So he modeled a different problem, a cantilever beam problem, onto a gear tooth, and then said, hey, let's use this methodology to design. And in the end, it worked pretty well because it was usually safer than it was, but obviously it was probably a little too safe. And there were also problems because it didn't always work in terms of fatigue strength and fatigue resistance as well. Now, one enhancement to his equation that we need to take into account before we start doing example problems is, because this is a static analysis and beam bending is a static analysis, we have to include dynamic effects. And the dynamic effects are very important because they realized once they started doing testing that the speed effects on strength are increased due to velocity. So if you increase the velocity of your gear rotation, you actually get a problem. You get a big problem with strength. So you need to have a correction factor or some correction associated with that. So we can write that the speed effects on strength are increased due to velocity. So what we need to do is we need to come up with a velocity factor and add it to our system, to our equation. So we're going to add this velocity factor called K sub V, velocity factor, and this K sub V is going to be multiplied by W sub T times P over F times capital Y, and this is going to be in US units. And most of the analysis that we're going to do in this module is going to be with US units because we're following the American Gear Manufacturers Association. So we're still going to write some equations for SI units, but we're mostly going to be focusing on US units, not necessarily for Lewis bending, but once we go into the AGMA method, which we'll talk about in the second part of this module. So for SI units, we would have an equation that would be very similar, but with module now, and we would have KV times WT divided by FYM, and this is in SI units, and F is going to be called the face width. So it's the face width of the tooth, or the part of the tooth that is taking the load, essentially. Now, in terms of the units for this equation, because this equation is unit sensitive, we have that WT is going to be equal to newtons, F is going to be in millimeters, M is going to be in millimeters as well, and sigma is going to come out in megapascals. Okay, now as a general rule, and this is something to keep in mind when you're doing projects and doing different work based on gears, is as a general rule, the F is usually 3 to 5 times your lowercase p. Okay, so it's 3 to 5 times your circular pitch, essentially, which is the distance between the teeth, just so you know the face width that you would need in terms of gear teeth that you would need. So it's actually wider than you would potentially think. Okay, so this gives us the equation for for our system and for KV. Now, one thing we'll look at once we start doing some examples is how we can find KV based on our different handouts. So we have some different equations based on our velocity, but we'll look at that through our handouts as well. So we'll see you in the next video in this module 2. And in the next video, we're going to be doing some examples based on the information that we talked about. We'll do some examples so that we understand what's happening. We're going to be doing 2 different examples to solve for the problems, one in SI units and one in US units. So we'll see you in the next video.